Hi, and welcome to Lesson 6 in our Chapter 1. Today, as you can see, we're going to be talking about transformations of functions. That means moving them around the coordinate plane and how those moves relate to the graph and to the equations, the function rules. So we just want to talk just a brief bit about the families of graphs that we will see in this class. You see two here that are linear. That guy I hope you're remembering. We have two polynomial functions and two root functions here that we're going to be talking about. And those are the families that we'll basically be working with. That said, a family of graphs is just a group of graphs that share common characteristics or common traits, just like you'd talk about in your own family. Maybe everybody has curly hair, etc. The parent graph is what I would call the basic model. Okay, that's if no changes have been made. And what I'd like to have us do is look at each of these, give the functions their names, and talk about the equation of the parent graph. And this one, the horizontal line, is called the constant function. Constant. Its equation would be something like this: y equals, well, this one is 0, but some constant. Okay, y equals some constant. This guy is called the identity function, and its equation is the line y equals x. Right? A combination of an identity and a constant gives us what we normally think of as a line, because this identity function gives the slope, this gives an intercept, if you will. Okay, that's very simplistic talking. This function, the v-shaped one, is the absolute value function, and its equation, y equals the absolute value of x. This is a parabola, and its parent model has the equation y equals x squared. In a broader sense, you could think about y equaling x to any even exponent here. Fourth power functions also have this shape, they're just narrower. This one is a square root function, and its equation is y is equal to the positive square root of x. This is a cubic function. Its equation is y equals x to the third power, but again, you could call this y equals odd exponent because any of them, fifth power, seventh power, again, have this same ribbony shape. They just get wider or skinnier. This is the cube root function. And in this case, y is equal to the cube root of x. And those are the functions that we'll deal with most frequently. Today what we want to do is take a look at how transformations to those functions affect rules and graphs. So I have several example problems up here. In this one, y equals x squared is the parent function. Here you can see we've negated that. We've given it the opposite sign. And what happens with that is that it is reflected over the x-axis. And most of us will remember that. Reflects over x, because we've had lots of experience with that particular transformation. It is sort of interesting to look down here. In the cubed function, the cubic, when we do that opposite of a cubic, we reflect over the x-axis. This branch moves up here, this flops down and comes up here. You'll notice that in this rule, the negative sign is applied to the entire function. Right? When we look at this one, it's similar, but this time we're doing the function but to the opposite of the value of x, that is, with the negative sign on the inside. That's what happened here. See, look at this. Still the parabola, the basic shape is the blue, but when you have that negative sign inside, then what you reflect over is the y-axis, not the x. Reflects over y. Again, this is kind of weird and it's hard to show examples of this. Notice that in the odd function, the cubic function, both of these guys look the same. When you reflect this over x, then you're talking this blue branch becomes that red branch. But when you reflect across y, then it's this way. This blue branch becomes this one. They look the same, right? Same thing is true here with the identity function. This is an odd function, so reflecting it over the x-axis produces exactly the same graph as if you reflect it over the y. I want to just point out to you again the difference between this is here the negative sign is inside, here it is outside. Very good. Next we want to talk about translations, and that's a slide. Many of us will remember the informal name is a slide. As you look at this function, the parent is the blue, and that's the parabola y equals x squared. The new rule here is x squared minus 3, and notice that it's dropped down by 3. In fact, every point on there that you can identify, right there, if you look, 1, 2, 3 down, that's mimicked right there. Every point is down 3. So subtracted constant on the outside of a function rule moves things down. In fact, everything goes down C units, whatever C happens to be. In our absolute value function, here's the parent in blue. We add 2. That moves everything up. Again, the addition and subtraction, so this one is up, C units. Here, the addition and subtraction are outside the function rule. Notice here, now we're inside the function. That is, we're not just doing f of x and then subtracting c. We're doing the function to x plus c here. The plus here, as in this one, here's the parent. Notice that it moved left. Everything here moved 2 units to the left. That's the opposite of what you would expect. Left, C units. Here we have a move to the right. We take the cube root function. Here's the parent. We move it 2 to the right, and a good way to think about it is that central point moves to right. So this one is a right-hand shift of C units. Those should seem very familiar to you because you talked about reflections and translations in your Algebra 2 class. The newer thing for us by far will be the dilation, and while you may have talked about dilations in your Algebra 2 class, you probably did not make the distinction between a dilation that is applied to the entire function or one that's applied only to the variable. Okay, so I want to have you number these 1, 2, 3, 4. And what I'd like to do is have you look up here and match a graph to each type rule. Here we have a multiplier that's multiplying the function rule, and we have that here. The multiplier is larger than 1, so this is an example of our first rule here. Notice that what happened to the parent function, the cubic function, is it got skinnier. It's growing taller faster. Folks, this is a vertical expansion, it's called. Vertical expansion. And a way to think about this that makes at least sense to me is that things get more vertical. That is, you're expanding in the vertical direction, you're growing taller faster. Here in this rule we have still a vertical dilation because the multiplier is on the outside, but now the constant value is some fraction between 0 and 1. Folks, that's going to be a vertical compression, it's called. Vertical compression. And what that will mean to in layman's terms is that you get less vertical. I want to pick that one, or have you pick that one out up here. We need to have a multiplier on the outside between 0 and 1. Oh, yes. So this matches the second rule. If you'll notice what happens, some people would say wider, and you would be right. Okay, that is a correct descriptor. However, what you're doing is becoming less vertical. See how it's pressing down toward the horizontal here? It's way more down around that origin than this one is. Less vertical. Vertical has to do with multipliers on the outside. When the multiplier gets inside the function rule, that's a horizontal dilation. So both of these last two are going to be horizontal dilations. And I'd like you to take a look for the one that looks like this. Inside multiplier greater than 1, which would make it this guy right here. As you look at that, this is now we want to think about this in terms of horizontal, what's happening horizontal, and I'll tell you what, this is getting less horizontal around the middle. See how it's going away from the horizontal axis? This is a horizontal compression. That is, it is less horizontal. The remaining picture here shows us a multiplier inside that is a fraction, and notice how wide that gets. It's getting way, way, way more horizontal there. This is a horizontal expansion because it is becoming more horizontal. One thing that I'd point out to you before we move on, notice that the horizontal dilations have a greater effect on the wideness or skinniness, right? These make more of a difference. More of a difference. And it makes sense in terms of mathematics, folks, because here you're raising not just x to the third power, but you're multiplying x, making it bigger by a power of 3. That's huge. This is going to have way more an effect on a graph than this. Okay, let's see if we can apply. So I'd like you to take a look at this. If we consider the parent function parabola, f of x equals x squared, and this transformation of that function, where, well, I want you to describe what's happening to this. In fact, I'd love it if you would pause the video and just write in words how the G graph will be different than the F graph. Here are my thoughts. The 2 here produces a vertical expansion. That is, it will get more vertical or become skinnier, if you will. The 1 here gives us the left movement. Remember, that goes the opposite of the way that you think it would. Okay, inside the parenthesis, that +1 is really moving things to the left. And then finally the constant down 3. Okay, that thing is added after the function part of it. That means it's a down. Now the next activity asks us to graph the function g of x, and I'll tell you folks, if all we had here were a left and down, what I would do is plot the parent function, the parabola, and we know how that one grows, and then just move points left and down. When you have that expansion in there, it makes it a little bit more difficult to do that, and I'm going to suggest in a case like this, you will be way better off to create a table of points, and remember our y's are going to be 2 times the quantity x plus 1 squared minus 3. So as we graph this, this is going to be a parabola. That means it has a bounce spot. Okay? It has a center, if you will. And that center will happen when what's in here equals 0. The only thing that will make this equal 0 is a -1 for x. That ought to be the middle point on our graph. Okay? So the middle x value is -1. Now, I know and you know that we're going to want to go a couple below that and a couple above it, and perhaps more, it's up to you, but at least a bounce point, two points below and 2 above. Now all we have to do is figure out what y will be when each of these values is used for x. Will you stop the video for a moment and do the arithmetic to find the y values here? Here are my values. Again, all I did was substitute x in and figure out, just grind out what the y will be. Now to graph that parabola, we just want to plot those points. Back 3, up 5. Back 2, up, down 1. At -1, so back 1, we're down 3. And then we have some symmetry going on. At 0, we're back to -1. At 1, we're up to 5. And you will see, folks, that we have a much more skinny version of our parabola. This thing is growing faster because of that vertical expansion. All right, I'm going to ask you to get out there, do the U-try, and we'll talk about this in school tomorrow.